The learning objective is I can identify conditions which lead to potential energy or kinetic energy being equal to zero. What this essentially is the ability to look at a situation and identify whether we have sources of kinetic energy or potential energy. And if we don't have them, we can set them to zero, which is going to be really useful in a future lesson. So to start with, to understand this, we're going to start with looking at a skateboarder in a half pipe. So skateboarder in a half pipe situation, you got the skater starting at the top of the half pipe and then reaching the bottom and then going back to the top. And you can kind of picture this in your mind. It's going like this motion. Back and forth, back and forth, back and forth. Now, when it reaches the top, it's turning around. And we know from our study of kinematics, right when it's turning around, right when it switches directions, if we have a velocity time graph, this velocity time graph is just passing through the origin right there. So its velocity is zero momentarily. That's going to set the kinetic energy to be equal to zero at the top. It starts with no kinetic energy because it's just starting from rest, dropping into the half pipe, and it goes on to the other side with kinetic energy being equal to zero. But let's take a look at gravitational potential energy. It's going to be maximized at these points. It is the furthest up it's going to be during this whole pattern, during this whole motion. Now, let's contrast that with right here, when the skateboarder is at the bottom of the half pipe. When it's at the bottom of the half pipe, it's not going to be going any lower. So we are setting the gravitational potential energy to be equal to zero at this point. And we're also going to set h is equal to zero. The height is equal to zero, which is of course why we get the gravitational potential energy is zero, is because we set h, the height, to be zero. And if our equation for gravitational potential energy is mgh, if we set h to zero, then the whole thing becomes zero. But its kinetic energy is going to be maximized. The skateboarder is going to be moving the fastest right here. And that kind of makes sense because as it starts, it has zero. But as gravity works on it, it's going to be picking up speed along the way. But as soon as it starts going up the ramp, now you have gravity fighting against it. So it's going to be getting slower and slower until it reaches the top where it stops moving altogether. We can represent this with bar graphs. Here we're going to have the energy, and in red we have the potential energy and the kinetic energy. And right now we're just talking about gravitational potential energy because that's the only source of potential energy we have. However, it's not the only source of potential energy out there. There's also spring potential energy, often called elastic potential energy. There's chemical potential energy, nuclear potential energy. There's lots of different types of potential energy. So gravitational potential energy, kinetic energy. And at the start, the bar graph looks like this, where we have maximum potential energy and no kinetic energy. And then we have, well, at the bottom of the ramp, we have zero potential energy and maximum kinetic energy. And then back at the top, we have maximum potential energy and zero kinetic. Now, one thing you should notice is that the height of these bars are remaining the same, which means however much potential energy it had to start with is how much kinetic energy it's going to get at a later time. If we were to draw these graphs, if we were to draw what this graph would look like, maybe let's say when the person is halfway down the pipe or so, it might look like something like this. Okay, your potential energy, kinetic energy, and a bar, and another bar, and they would be at equal heights. But more importantly, if you were to stack these two on top of each other, they would equal the same height as the maximum values. The total amount of kinetic energy is not going to change. That's actually for a future lesson, conservation of kinetic energy. Let's talk about more situations where we're going to talk about zero gravitational potential energy. If the formula for potential energy is mgh, then when h is zero, gravitational potential energy is zero. That's assuming that mass isn't zero. So therefore, the only thing that could be zero in this equation, realistically, in everyday situations, is the height. Here's the problem though. How do you define height? You might say, well, when it hits the ground. And that could be useful. But there are situations sometimes where the height being defined places other than the ground or other than the lowest value being zero makes sense. Let's take this situation right here where we have this roller coaster. Where should we set a height of zero? What makes the most sense? Now, I think most people would agree that height of zero does not make any sense to put at the top of the roller coaster. Now, you can do this and the math works out just fine, but it's not the most convenient. It doesn't make the most sense to us. Now, this roller coaster dips down and goes back up before stopping. You could set the height of 0 at the bottom of this ramp, at the lowest point this goes. That would be a valid place to put it. However, I would argue that it would be easier to set the height of 0 to be where it ends. Because let's remember that what we care about most is the change in potential energy, which is going to equal mg times the final height minus the initial height. And boy, would it sure be really convenient if one of these values was struck out to be 0. So if we set the 0 value to be here, where it's just passing through, then neither of these values are going to be 0. Since we are free to declare where the 0 point is for height, let's imagine the same situation described previously with the roller coaster, but we're going to declare 0 at 3 different places. The first one is going to be at the bottom, the lowest point. The second one's going to be at the top, and the third one's going to be at the end of the roller coaster. What we're going to determine is what the change in potential energy that an object experiences if they were to go through this roller coaster. And it's going to use the equation mg delta h, or if we just want to break out that delta to what it means, mg h final minus h initial. So for the first one, this object is at 5 meters to start with and ends at 3 meters. So mg h final is 3 meters minus 5 meters h initial. And what we get is negative mg times 2 meters. Or just to rearrange this, negative 2 meters mg. Now, that's meters and that's mass, so those are different units. But ultimately, the value is going to be negative 2 meters times whatever mg is. Let's compare that to when we have the initial height being 0. So we have the change of potential energy is equal to mg, and what we have is the final height minus the initial height. And we're saying the initial height is 0, and the final height is negative 2 meters. So we get mg times negative 2 meters. Again, we'll just rearrange that, negative 2 meters times mg. Oh, whoa, would you look at that? Those two are the same. And you're seeing a pattern, you might suspect it's probably going to be the same no matter where we place the 0 meters. So let's just check that with the last one. For the last one, we have a change in potential energy is equal to mass times gravity times the final height minus the initial height. And what we're saying is that the final height is actually 0 this time. So we get mg minus, and the initial height was 2 meters. So sure enough, the change of potential energy is negative 2 meters times mg, mass times the gravitational acceleration constant, which again is equal. And that's because no matter where we declare the height of 0 to be, this object is still going to lose, and that's why the negative value is there. It's still going to lose the same amount of gravitational potential energy. Now, it didn't lose that energy. We know that it's going to become kinetic energy. So whatever kinetic energy it has at the very end of the track is based on that negative 2 meters times mass times gravitational acceleration constant. So it doesn't matter where you place the 0. But I would argue that this configuration right here makes this problem easier. You set your final height to be 0. It's where you're going to end up. As long as one of these is 0, it makes it really easy because you don't have a subtraction. This first one, you had to subtract the two numbers. You get the same value in the end, but it's a lot easier if you could just make one of them 0. And if you make the starting one, in most problems, the positive value, and because your final one's 0, then you're going to most likely work more often, at least, with positive values. And that just makes our lives easier. Again, the value gets the same no matter what. But I would argue that this configuration is the most convenient. So whenever you're approaching a physics problem using gravitational potential energy, you should first declare where your 0 height is and try to think of what would be the most convenient for you.